doing? Ready for the weekend? Yeah. All right, so remember we have exam on Friday. Not Friday, Monday, today's Friday, whatever it is. So the exam again covers rational functions back in 3.7, and then the stuff that we've done in chapter 4 with exponentials and logarithmic functions. We're going to finish up the models today. Remember, there's 2 review sheets on Moodle as well as a practice exam, and the practice exam is literally the exam that I gave last year when I taught this class. Okay, so if you want an idea of what the test might look like, that's what the test might look like. All right. Any questions at all before we finish up talking about models today? All right, so last time we were working on this problem where we had a bacteria population that tripled every 27 minutes. The first part asked us to figure out an equation for the population at time t, where t was in minutes. The directions said round to 3 decimal places, but we just wrote the final function where we didn't need to worry about the 3 decimal places. We just wrote it as a power of 3. If we were following those directions, we would want to put that 3 to the 127th power in your calculator and get those particular decimals. Some things to notice. Notice that the projector went off. Notice that it was telling us something about tripling time, right? It triples every 27 minutes. Notice that your base for your exponential function in that case is a 3. And that comes up from this expression here, this equation that we set up. Also notice that it told us it tripled every 27 minutes. So notice that we had a 27 in the denominator. That makes sense because if I put 27 now in for t in my exponent, I get a 1, so I get 3 times as much as I started. If I put 54 in for t, which is 27 plus 27, or 2 27s, right? I would get 3 squared, which makes it 3 times another 3, or 9 times as big, and so on down the line. All right, so it's not a huge surprise that's what that looked like. So let's look at part B. It wants us to find the population after 1.5 hours. In order to do that, do you want to plug something in for t, or do you want to solve for t? Put something in for t, right? In this case, what do we want to put in for t? T is measured in minutes, so what do we want to plug in for t in this case? 90, right? Because I got to convert that to hours to minutes, right? So in this case, you would have p of 90. And in this case, you really would want to put that in the calculator. You're going to round to the nearest bacterium. So what do you get when you put that in your calculator? Anybody get a value? $15,420. Okay. If you wanted a quick check, notice that if you had 81 over 27, that would be 3 times, that would have a power of 3 there, which means if you multiply that by 27, 400 times 30 is about 12,000. So that 15,000 kind of makes sense. We're just going to do a quick check. Because 90 over 27 is bigger than 81 over 27. So that got a little bit bigger. Makes sense. This one okay? All right. Let's look at the next one here. this one is asking us to actually model what looks like exponential decay. When it's talking about half-life of a particular atom, it tells you the amount of time it takes for half of the atoms to go away. That's what exponential decay is, or in terms of atoms at least. All right, so in 12.3 years, you would have half as many atoms as what you started with. Okay? So rather than doing a doubling or a tripling, in this case, we're halving. Okay. So again, if I go back up, when we did this one where we had a tripling time, notice that the base of our exponential here was a 3, right? If we're doing a halving time for a half-life, what do you think the base of our exponential function is probably going to be? 1/2. Yeah, exactly. Okay. So let's see where that comes about. We don't know how much we're starting with, because that's what that a sub 0, that a naught value is. But if we start with a naught, we know that in 12.3 years, we're supposed to be half of what we started with. That's kind of our defining equation there, right? T is measured in years in this case. It tells us that in 12.3 years, we have half of what we started with. Remember that coefficient that's out in front? Whatever that coefficient happens to be here, that's our initial amount that we start with. Because if you put 0 in for t, no matter what the base is, if you put 0 in for t, you're going to get 1 for that. Okay? So that coefficient that's out in front of the exponential function is how much you start with. The problem tells us that in 12.3 years, we have half of what we started with. So notice now, if I plug this in to the form of the equation that we have, we'll have a naught times a to the 12.3 equals 1/2 of a naught. What should we do next if we're going to try to figure out what a is? What would we do next? Yeah, the a naughts, right? Yeah, divide out that a naught. So they have a to the 12.3 equals 1/2. And notice, I'm going to scroll back up real quick. Notice that looks a lot like the equation that we had in the previous example here, right? So notice that we're going to get that same base idea that we had. So I need to get rid of that 12.3 power. To get rid of the 12.3 power, what do we want? Yes?
Is it always going to be like that? Like, can we just go ahead and put a to 12.3?
Yeah, it's always going to be like that. Exactly right. Yep. What are we going to do to both sides to get a by itself then? What are we going to? Yeah, do the 12.3 root of both sides, or raise both sides to the 1 over 12.3 power. Now, in this case, again, the problem asks you to round to 6 decimal places, but this is what the base has to be. If you want to figure it out to 6 decimal places, you would type that into your calculator and use that for the a. But if we just leave it like that, then your function just becomes a naught times 1/2 to the t over 12.3. Because again, I would plug in this 1/2 to that power, and then raise that to the t power. You multiply your exponents in that case. And then again, look at this compared to the previous problems we did. We have a 1/2 because we're given half-life. In the previous example, we had a 3 because we were given tripling time, right? Notice in the denominator, 12.3 is how long it took for it to have. In the previous example, 27 was in the denominator because that was how long it took to triple. And that's what's going to happen every single time in these types of problems. Every time. All right, so in part B now that we have the form of the function, in part B, it says how much of a 5-gram sample is left in 5 years. So we have a 5-gram sample. What number does that represent? The A naught. Yeah, this is your initial amount, so that will be your A naught. This is what we're going to plug in for T. Yeah. So we want A of 5 in this case. So that would be 5 times 1/2 to the 5 divided by 12.3. What do you get when you put all that in your calculator?
3.772.
Say it again?
3.772.
3.772, is that what you said? So what others got? And in this case, the units would be what? This is an amount of stuff. In this case, what amount is it? What's the unit that the stuff, that hydrogen is given? It's grams, yeah. So it would be 3.772 grams. The only thing different between this part B and part C would be what? Instead of plugging in 5 for T, you would plug in 7 for T. Yeah. So part C is exactly the same, just plug in a different number. Questions on that one? Okay. So the next one's a little bit different. The next one we have infant mortality rate given to us by deaths in deaths in each 1,000 live births in the United States. It was 7.6 in 1995 and 7.2 in 1996. So this one says, assuming that we have an exponential model, which means that just assuming that we have this form for our function, we want to find a model that describes the mortality rate a certain number of years after 1995. So what that means is that t equals 0 corresponds to 1995. If we're going to use t equal to 0 corresponding to 1995, then what number can we plug in right away? 7.6 for the what? The A naught. Exactly right. Yep, we can plug the 7.6 in for that A naught, right? So using t equal to 0 to represent, if I can spell, 1995, then we have A of t is 7.6 A to the t. So we've got one of those pieces. The other piece that we need to figure out is the A, right? We need to figure out what this base is. So this is going to be a little bit, not too much different, but a little bit different. The other piece of information that we're given is that in 1996, the infant mortality rate was 7.2. Well, what t corresponds to 1996? 1, right? So this says that when we plug in 1, we're supposed to get out 7.2. So what equation are we going to set up here? Good. Exactly right. Yep. So this tells us that when we plug in 1, we're supposed to get out 7.2. When we plug in 1, we get 7.6 to the 7.6 a to the first power equals 7.2. Can we solve that for a pretty easily?
Just divide, right? And you could get a decimal approximation for that, but I want to leave the decimals for the end. That fraction. Notice that I can move the decimal place one place to the right for both of those. On top and bottom, it has the same effect as multiplying top and bottom by 10. It's 72 over 76, and 4 goes into both of them. So I can reduce it to 18 over 19. So our final function then would be 7.6 times 18 over 19 to the t power.
I wouldn't, if you just want to leave it at 7.2 over 7.6 and plug that in right there, that's perfectly fine. Maybe a little bit easier. Part B asks you, what will the infant mortality rate be in 2025? So what do we need to do to figure out what the infant mortality rate will be in 2025 according to this model? Exactly. That's exactly right. So t equal to 0 corresponds to 1990. So what t value will you use to represent 2025? 30. Good. So we want to figure out what a of 30 is. So t equal to 30 corresponds to the 2025. So we'll plug in 30 for t. And this one asks us to round to one decimal place. What do we get in that case? 1.5? So notice that our process, pardon me, notice that our process in every single one of these problems is to try to figure out the two values and then use our model from there. That's okay? Well, let's see if we can do the next one here. So we originally have 134 rabbits being released into some area. The free of predators part is just telling us that the rabbits will be able to grow unchecked. Essentially, they won't have any natural occurring things outside that's going to reduce their population, and so that's why we're assuming the exponential growth. If you had outside influences that would hinder the rabbits from growing, then you would have to make adjustments to your model. So everything here, we're not going to worry about the adjustments to the model piece. Okay. All right. So we have 134 rabbits that come in. In 3 years, the population has grown to 1,072. So let's use that information first to set up our model. And then we'll worry about answering the question. We'll get the model set up, and then we'll worry about answering the question. If you can, you should try to identify what the initial amount is to start. What is it in this case? 134, right? It says that there's 134 rabbits being released into an isolated area. So we know that our A naught should be 134 to start with.
Then we want to figure out what the base of our exponential function is. We would need to use that other piece of information that we're given. It says after 3 years, the rabbit population has increased to 1,072. How do we use that information to help us figure out what the A is? What do we need to do? Good, exactly right. So this says that when we plug in 3, we're supposed to get out 1,072. Right? That's what that second piece of information says, doesn't it? After 3 years, there's 1,072 rabbits. When we plug in 3 for t, we get a 134a cubed equals 1,072. What do we need to do to solve for a? Get divide. And then take the cube root. Cube root I can write as a 1/3 power. So that when I go back in here and plug it in for a, I would multiply by exponents again, right? You'd have a 1/3 power and then raised to the t power. So I can write this as 134 times 1,072 over 134 to the t over 3 power. I mean, if you want, you can get a decimal approximation for that and just plug it in for a. If you do that as you're going through multiple steps of the problem, I would make sure you keep as many decimal places as you can in your calculator. In particular, if you're doing, pardon me, exponential growth or exponential decay, the more you round, you can get really, really big errors at the end because you're doing exponents on an error. The higher the exponent, the more error you're going to get as you go through. So if you leave it as fractions like this and then type it in each time for your calculator, then you won't get as many errors. Are we okay with setting up the model? This should look a lot like what we've done in the last several problems, right? Now let's do what the problem actually asks us for. After another 6 months, it's asking what, and it means another 6 months past when it's increased to 1,072. In another 6 months, what will the population be? So what do we want to plug in something for t or solve for t? Plug something in for t, right? Because we're trying to get an amount. What number do we want to plug in for t in this case? Okay, so it says that, notice it says another 6 months, right? So there's going to be a 0.5 involved in there. It'd be 3.5. Good. It's another 6 months past the 3-year point. That's exactly right. So we want to plug in 3.5. So I can write a little bit neater so you can actually see what I'm writing here. So yeah, we want to actually plug in 3.5 for the t. If you would have just plugged in 0.5, you would have got a number smaller than 1,072, which wouldn't have made any sense. It should have grown more past that point. And this one's asking us to round to the nearest rabbit. What questions do you have on that one? This one okay? All right. So the next one, this is the next few are just giving us other applications of problems that either are exponential functions or look like exponential functions, but not quite that exponential form. So in this one, it's telling us that we can model the price of a product if we know what the yearly inflation rate is. So notice that the form looks like 1 plus r raised to the t power. The reason for that particular form, just to talk about why it looks like that, if you had something that costs $10 now, and you know that inflation was 5%, if you wanted to know what it cost in a year, what would I have to do? Well, I'd have to figure out how much it raised, right? And then add on the original cost, because that first part is just how much did it raise, right? And notice in that case, you could factor a 10 off of both of them and write it in that form, correct? Because there's a common factor of 10 in both of them. I know I flip-flopped the numbers in the middle, right? So notice that this was the initial cost here, and this was your inflation rate, and that's what fits that little pieces up there, doesn't it? So inflation rates are good things to model with exponential functions, because it's what you have is a compounding effect from that percentage year over year over year. All right, so let's say we have an inflation rate that's 2.5%. It wants to know what's the cost of a motorcycle that's a little over $20,000 now. What will that be in 8 years? So here is the inflation rate. So what's the inside of our model going to look like to start with? We'll worry about the C naught in a second. What's the inside of your model going to look like if you have an inflation rate of 2.5%? What's going to go on the inside? Yeah, 1 plus. How do we represent the 2.5% as a decimal? Not quite 0.25, but by 0.025, right? So on the inside, we'll get 1.025. When we add the 1 and the 0.025, we can combine those same piece there. The C naught, again, just like in the previous examples, that C naught represents an initial amount. In this case, it's an initial cost. We're trying to figure out how much a $20,400 motorcycle will cost in 8 years. What are we going to use for the initial cost? $20,400. Good. So this would be our model for how much the motorcycle will cost after T years. We want to know how much it'll cost after 8 years. So what do we need to do to figure out how much it'll cost after 8 years? Yeah, plug in the 8 for T. Good. And what do you get when you plug in 8 for T there? 24,855, 40 cents, 42 cents. Okay. I got almost all the things you said. But notice that the setup here is just like what we did before in the previous problems, right? Figure out the initial amount, figure out what the base is. In this case, figuring out what the base is a little bit easier because they tell you what the form of the base is, and you just have to plug in the inflation rate. What questions do you have on that one? It's all right. Let's look at these next ones here. Notice that in the next couple of examples, they're not quite exponential functions, right? This first one has a piece of an exponential function here, but I'm subtracting it from 1 and then multiplying it by something else, correct? So it's not quite an exponential function, but it's got a piece of it. And notice that the next one also is the same idea. We have, pardon me, something that has an exponential function down at the bottom, but it has some other things going on. So what we're doing here with these is making up a different type of model that allows us to not assume that we've got something that's growing all the time or decaying all the time. So in this case, it says it's giving us the concentration of a drug in the bloodstream after a certain time. Well, notice that if you put in 0 for t, well, we get e to the 0. Well, anything to the 0 power is 1. 1 minus 1 will give you 0. So there's no drug in the bloodstream to start with, right? Let's look at just this piece right here for a second, just that exponential piece. Because this goes back and reviews a little bit of stuff that we did with transformations and graphs. Okay. If I were just looking at this little piece and just wanted to do transformations of graphs, what would you use for your base graph? E, right? I'll do e to the x. Exponential functions either go this way or this way, right? What's the difference between going up or going down? What tells you the difference between those? If the base is a flipping point, right? Is it going up and going down and it depends on the base? Where's that flipping point at? Not sure that we're doing it, right? Where's that flipping point at? It's 1, right? Yeah, we've got some that go like this and some that go like that, right? Oops, not quite like that. It goes that way, doesn't it? There's a flipping point with the base, right? This one that goes up all the time, the base is greater than 1. This one is between 0, right? Okay, so if we're doing e to the x, then it's going to be the one that goes up, right? What does this negative tell you to do right here? It flips it left to right, doesn't it? Across the y-axis. If you flip it across the y-axis, this one's going to go like this, isn't it? And then the other one's a horizontal compression, but that's not going to change whether or not it goes up or down, right? So this particular graph goes down and to the right, right? Just using our transformation of graphs idea. In particular, the farther you go out to right, the y values get closer and closer to what? 0, right? If the y values get closer and closer to 0, this 1 minus that's going to get closer and closer to 1, which means the whole expression will get closer and closer to 0.04. So what this is doing is it's modeling something in the bloodstream. It's just saying that initially it'll go up pretty quickly, but it's going to end up flattening out as you go out. That's what this model looks like. You wouldn't want a drug in the bloodstream to go like this, would you? No, because eventually you're going to go like this, and then it's going to, you die. Right? That's what's going to happen, isn't it? Okay? So if you're putting a concentration of drug in a bloodstream, you want it to level off, especially if you're trying to do something like antibiotics and try to kill off bacteria in your body, trying to kill off an infection. You want to have a certain amount in your bloodstream all the time so that it kills the infection off, which is why when you take doses of antibiotics, you do it every so often so it keeps that kind of constant amount of drug in your bloodstream. Because anytime you put something in your bloodstream, of course, your liver is going to try to kick it out. That's what your liver does, right? Filters out toxins and some other things, but it's one of the big things it does, which is why it doesn't like alcohol very much. All right, in any event, this problem is just asking what's the concentration after 20 minutes. So what do you want to do in this one? Yeah, it's just it wants you to plug in the 20. Good. So if you want to do the concentration after 20 minutes, you just plug that in. And get what in this case? Okay. Questions on that at all? That one wasn't too bad, right? It literally just wanted you to plug in a number and get out a value. But I wanted to explain why this is another use of exponential models, because it is modeling something that's going to level off over time. And that's exactly what this next one does as well in the next example. If we look at that e to the negative t, we've got this situation again, don't we? Whereas the farther you go out, the smaller it gets. So this part right here in the denominator, this 999 e to the negative t, that will get really, really small, which means your denominator is going to get closer and closer to 1, which means the whole expression will get closer and closer to 9,000. So what that means is that as you go out, what this model is going to do is it's going to go up and it's going to level off again. This is an example of something that's referred to as a logistic model, and it's good for modeling populations with limited resources. Eventually, there's going to be a carrying capacity issue, meaning there's only going to be so many resources around that can sustain a certain population. So that's what logistic models do. This is an example of that. You're not going to have to create them on your own. If you're given a model like this, you'll literally be given the function. Okay? That's why we're talking about these types of functions, is because they're very, very useful in modeling different situations. All right. So we've got the number of people in a town that caught the flu. Okay. So this one's asking us how many people were sick initially. How many people of the initial outbreak had the flu? Well, what do you plug in for t if you're looking for an initial amount? 0, right? So in this case, we'll want n of 0. Well, the opposite of 0 is 0. Good. E to the 0 is 1. 999 times 1 is 99, plus 1 is 1,000. So we get 9,000 divided by 1,000 gives us 9. Good. Didn't actually need a calculator for that one. Also don't need to round to the nearest person because it was exactly 9 is what we got. So this would be, just to give a context of something where this might actually matter. Say you've got a group of people coming over from a foreign country on an airplane, and maybe they caught something in a different country, and they came out. 9 of them were sick on the plane. So now you've got 9 people introduced into the population that were ill. And you want to see how it spreads. So this actually is stuff that people do if they're trying to model spreads and outbreaks, and why they try to take remediation measures to do all these things, which you probably remember all too well with, masking and social distancing and all of that stuff. All right, anyway, that's what the amount initially there. How many people caught the flu after 4 weeks? The T is representing weeks in this case, so how are we going to figure out how many people caught the flu after 4 weeks? Plug in 4 for T, good. Pardon me. Plug in 4 for T. That's just a matter of plugging everything in the right spots in your calculator. Make sure when you're typing these things into your calculator, you've got your entire denominator in parentheses. So maybe you've got something to type like that in your calculator. Or if your calculator bumps up your exponent into where it should be when you're looking at it, then you can just type in -4 there. But definitely make sure you have parentheses around your entire denominator. That's important. Again, unless you have a calculator that puts it into a fraction form to start with, and you don't have to worry about your parentheses as much. If you're unsure where your E button is on your calculator, it's usually right directly above your natural log button. So you have to use your second to get up there, or shift, or whatever your calculator looks like on there. What do you get for that? 466. So what others got? Ooh, 4,200. That's a lot different. Let's see. I'll type it in my calculator, see what I get. I got 466. Let's try to retype it back in and see what you get. Any question on the process on that one? The last part is just asking us to interpret what I mentioned at the beginning here. So I'll just rewrite the function down here. So remember that this notation again just means it's a kind of that end behavior notation. It's saying what happens as t gets big, right? So we've already established e to the negative t goes this way, right? Goes this way because that negative sign would flip your original graph left to right. So it goes that way. Okay. So as t gets really, really big, e to the negative t gets really, really small. So it goes to 0, right? That would be the end behavior for that particular function. The bigger the exponent gets, this expression gets really, really small. Okay? So if e to the t gets really, really small, then what can I say about the function? What's it going to go to? So this part right here goes to 0, gets really, really small. If it gets really, really, really small, if I multiply by 999, is that going to have a lot of effect? No. So that's also going to be really, really small. And you add 1 to it. So what's the denominator getting close to? 1, right? So this is going to get it closer and closer to 9,000 over 1 plus 0. Just replacing that last chunk with a 0, and we get closer and closer to 9,000. In disease modeling, this would be the example of something becoming what's referred to as endemic in the population. There's always a certain amount of people in the population that are sick with the disease at any given time. That's what endemic means. So things like flu are endemic. Now, of course, depending on seasonal, it does drop up and down. But there's always a certain amount of people who are sick all the time. Not the same people, but there's a certain number of people, right? It's not saying the same people are sick all the time. It's just saying there's a certain number of the population that are sick all the time. So in this particular model, eventually in the population there will be 9,000 people who have flu at any given time. That's what that says. And again, this is one of the importance of exponential functions. People do these things in the real world to help to do things like disease modeling. If you don't like to think about disease modeling, biologists do it for population modeling. Business people do it for financial modeling, like inflation modeling or stock market modeling or any of those kinds of things. Honest to goodness, people do exponentials and logs in real life. Okay? So we really do these. So they're very important functions. Any questions on this one at all? All right, so again, your exam is on Monday. The one section that's different from the rest, that's not exponential and logs, is a rational function problem, right? So when you have a rational function, finding your intercepts, finding your asymptotes, being able to sketch from that information would be one problem like that. Then we had exponential and log graphs. Don't forget those. Being able to compute values of logarithms, simplifying those things. And then the last stuff that we talked about right before this was solving equations with exponentials and logs. So again, you've got 2 reviews on Moodle plus a practice exam. And again, like I said at the beginning of class, that's the exam I gave a year ago. Okay? So if you want to know, what does an exam look like over this particular chapter? That's what the exam looks like over this particular chapter. Okay? Literally the exam I gave last time. All right? All right. Have a good one. I'll see you on Monday. Have a good weekend.